Welcome to Chapter 4. This is motion in 2 dimensions. So I'm Sorasak Phanphak, your instructor. So you will have learned about the motion of the particle, which is represent the objects or thing that you interest moving in 2D space of our 3D world. So what is about moving in 2 dimensions? So we did learn linear motion, right? Moving in 1 dimension as the object moving along x-axis. Now we expand our knowledge to like a real world representation. It may be supposed to be in 3 dimensions, but with these 2 unique type of motion. The first one is projectile, and the second one is the circular motion. With 2 of them, you can investigate what is happening in 2D. So as you see, this is the part that Steph shooting the ball out, and the curve is come as a parabolic curve as a projectile motion. With this young girl, she swing around this central, and the reason that she is moving in like circular plane because the force that attract her to get inside, we call this as a centrifugal force. We will learn about these 2 motion today. As I said, like we have all this motion in our 3D world, but if you look after like this like projectile motion and this uniform circular motion on a uniform, if the tangential velocity is not constant, we can look into like 2D space. For this case, if this our x, y, and z in the Cartesian coordinate, we can see this is the motion, whether it's in y, z or y z direction or x z direction. You can explain motion of the projectile in 1 planar. So this is like happen in 2D space. So how about this circular motion? I will move this forward because we represent this as the y-axis. So I have y and z here. For how about the circular motion? You can see it's moving along the plane. So this is kind of like this circular motion happen only in the x and y axis. So this is the kind of like planar of this motion that happen. It's not only happen in like x, y. It can be happen in any plane. But remind that we are looking after 2D motion of this particle specifically, but what is happen in our 3D world. So before going to in-depth explanation, we have to come back to the vectors, because all the parameters that we're gonna state about, although even the position, displacement, velocity, and acceleration, they are vector. So keep it in mind, because when you represent about the motion of object changing to st is like the curve or path or the displacement moving, you have to account all these parts as a vector, and you represent individual position by using the position vector. If this point, I represent like r1 as a position vector. This is position vector. And when you have the position change, it's got some displacement, and this can be a path or displacement. It's depend on in which gap you're looking after. How about this? Although you have a 3D space, right? 3D space like this, you can just ignore some part of the space, as I stated before, if this happen only in 2D space. So now you can represent this as maybe xi plus yj plus zk as a vector in 3 dimensions, right? Now you have a plane only in y and z. So this is vector, the position vector, you can represent it only as the 0i plus yj and plus c or zk. So here is can be complete with just these two components, whether it's yj or plus zk. That's it. This is your S to represent these are the position of this fly movement. So now we going back to the definition of our displacement, velocity, and acceleration. All these are vectors. If you see it in bold or with the arrow size on top of it, make sure you know it as a vector. So you have the definition of the position vector. No need to position, no. A position vector as R or vector R here. When you investigate the chain of the position, you got the displacement. So displacement is what state about the initial point, right, to the final point. That is your vector. So this is your displacement. So if you have the change of the position with the time, which is this delta r is your displacement, over the time you got velocities. Moreover, when you have the velocity and you like to convert to the acceleration, you can dip with the time, right? When you convert the position with to the velocity, you dip with the time. Now you got the acceleration, which is the change of velocity against time. I will define this as instantaneous. N-E-O-U-S. Sorry, I will write again. As an instantaneous of the velocity and acceleration, because what you would like to investigate here is as a velocity at any time point and acceleration at any time point as well. So these are all instant. And you remember, you also have another definition of the average. I will redefine it by this slide. So this is the definition, the comparison between a position and a displacement, right? When you have the position change from initial point to the final point, the change of it, like Rf minus Ri, is your displacement. It's different from the path or distance, right? The distance is the orange line, but when this angle is quite small, so you can see that the path or the displacement is mostly unequal. I will explain this more soon. So this is the definition. If you have the vector components, because you learned in the vector chapters already, right? When you have the vector r, if you know the angle of it, you can get the component of rx and ry, right, by r cos theta and r sin theta. And these components, if you would like to find the delta r, you can subtract them immediately if they have like in the same axis, like in I, in the same axis as in J. So finally you get delta r or displacement as the x2 minus x1 in I direction and y2 minus y1 in j direction. And this is the different definition of position to the displacement, because the displacement is a change of position. Now, if we get the position to the displacement, right? If you would like to find the average velocities, you can divide with the time that they change. This is the average. What average determine is the difference between one position to another position. If you can find the delta R, for example, like delta R1 or delta R2 or delta R3 here, the difference of position divided by time is your average velocities. However, the instantaneous velocity is come from when you would like to find at some specific point. For example, at point A, if you would like to define only this position, you lower the gap of the time that you want close to zeros. That means you would like to find the infinitesimal time, right? So with this, you diff R or the position vector with the times. So R is supposed to be a function of time as well. So when you dip it, you got the velocity at any time point. This is your instantaneous velocity. And what I remind you, when you see this bold alphabet, thinking is that having the arrow signs on top of it, so it's all vectors, right? And the direction of the V is along with the chain of the R vectors. So how about the average and instantaneous acceleration? If you have the chain of the velocity like this, like initial V, the final V, so the chain you got the final V and minus of the initial V. This is your final V. So now what you get this is your delta V, right? And when it's moving like this, the direction of the delta V is your direction of A. So to get an A average, the average of the acceleration, you get the delta V over delta T. If you would like to find the instantaneous, like A at any times, so you do the differentiation V compare to dt. So V by dt is got the AT as similar to, if you like to find the VT, you diff RT dt. And this is the relation of the displacement to position, the average velocity to instantaneous velocity, and also the instantaneous acceleration to the average acceleration in terms of vectors. Now you have to look after all these as a 2 or 3D vector, right? All of your V, S, or A also have components in I, J, K as a vector. Right, don't forget about the arrow size or the definition of the vectors. Now, from the example 1, how can we solve this problem using the knowledge of the vectors and all the relation of the displacement, velocities, and the acceleration? So this particle, is that about this particle move from a less position, the particle have something act to it, and this particle is moved. So the initial position, like R0, is 3I plus 2J. This is like initial position. It has been accelerated with some force. So the x acceleration is 5 plus 6t in k direction. So I may write it wrongly. I will write like this is on some, if 3D diagram like this x, y, and z. A is like over here on C direction. How about R zeros? Maybe it's supposed to be along this planar. This is on XY planar. So it's still on XY planar. And this is on Z direction as A. So determine the position vector of pointing at the particle at any times. So what is one here in this question? You have the frame of reference asking this, and this particle, the red particle, moving like around this. So you need to find the position vector like R that depend on T to identify all these particles moving along the path with the times. This is the job that this problem asking you to solve it. So how to do this? Let's start from the definition that we have learned about the instantaneous, because we see this like, okay, instantaneous A, and this is maybe the initial position vector. So from this, we know A is what is have come from is from dv by dt, right? When A is instantaneous acceleration and V is also the instantaneous velocities. So by this, if we would like to find the V, you can rearrange this term. So you can get the dv equal to a t dt, and then integrate dv and also a dt. Your job is to put to put the limit in. So you can integrate from initial velocity to any instant velocities. So also with the time, like initial time t0, maybe get it as zeros, and the initial t, instantaneous t as a t. This is how you set the integration form for finding the velocities. So after you integrate this term, you get v and put a limit from v0 to vt, because this is represent the instantaneous velocity, and also integrate the at. So here an at is 5 plus 6tk. This is what you got from and integrate by dt from 0 to t. So now you got this term as 5t plus 6t over 2 and divide by 2. Don't forget to put a limit in from 0 to t and from 0 to t. All of them in k direction. This is after integral. And you sub all the limit in. And what is happened? This particle is moved from a rest position. So rest position means v0 is equal to 0, right? So that another definition here is v0 is equal to 0 meter per second. This is another condition for this motion. So finally, in this part, we got Vt minus V0, which is 0. So ignore it. And you sub all this in is 5t, and 0 is 0. Don't care about it. And plus 3t squared. All of these in k direction. This is your V in any time point. So this is your instantaneous velocities, right? But your job is to find the instantaneous position. So your job is to find RT. So let's continue after that. This is the first part of finding the VT. Your second job is to find the RT. As you know, the VT is come from the diff of the position vector by dt, and this position vector is supposed to be function with the times. So it's called instantaneous position vector. So by this you can rearrange like you did before. So now rearrange it. So you got dr equal to vt dt. Then let's do some integration. So you will get, I will change the color because the mix up of the top type of the color. So integrate this from maybe from R0 to R. R0 is like initial position, because we got some condition here like initial position. So this is your R0s. Mark it, and then you will use it later. And Vt, what you would like to integrate, you integrate from the 0 time point to any time point, so that this can be your RT, because this is at any time point. So after the integration, so you got R with the limit of R0 to RT, then equal to the Vt term, which is, I will put the Vt which is we found here, that is 5t plus 3t squared in k direction. We do some integration by dt, that is 0 to t. And we can perform the integration from this part. So it's 5t squared. When you got the squared up, you have to multiply, divide by the factor that you integrated up to, and this is 3t cubed, and you have to divide by the order of that magnitude. Don't forget to take a limit in from 0 to t, and also from 0 to t. All of these are in k direction. So that this r is your vector, this r is your vector now. So put the limit in by the substitution of the value. So what you're gonna get finally you're gonna get t here minus r0 equal to this part is 5/2 t squared plus 3 cubed in k direction. So now the final job is to replace this r with this condition, right? We know the condition over here. So now put it in. So finally, I will change the final color. The RT that you're gonna get is equal to the R0 here. You put it, so it's gonna be plus over here. So it's 3i plus 2j, and finally you got 5/2 t squared plus 3t cubed in k direction, and unit is meter. Right. This is how you get the position vector at any time point. So this is represent the position of the object on this one moving along this part when it has been and caused by this acceleration moving from the rest position to final position.